Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to start work on the first true mechanical component of the Pennsylvania A3 switcher locomotive. It's the first of two water pumps. Locomotives always need at least two water pumps or two methods of getting water into the boiler because of course the water around the coal fire is the only thing that keeps the coal fire from melting holes in the boiler and making it explode. So it's a very important component. Let's go. Here's an example of the type of piston pump that we will be building today. It's a very common style. There's a valve body running vertically at the front, and then there's a piston that slides back and forth in the bore back here. When the pump handle is drawn back, the piston draws water in through a lower check valve. Then when you push the handle forward, the water is pushed back out of the bore, up through the upper check valve, and onto the destination. So it's just a series of check valves and a piston. That's all you need to shift water. However, just shifting water is not enough. On a locomotive, the water pump has to be able to force water in against boiler pressure, which can be as high as 200 psi. That's why we use piston pumps for this, because they're extremely robust and reliable, and it can handle the pressures compared to something like a rotary gear pump where it's very difficult to make one that can handle these kinds of pressures. Here's Kozo's design for the hand pump in the A3. It's very similar except that it's about half the size, and it's fabricated instead of being made from a casting like the PMR pump that I just showed you. And what's really cool is I think I can build this entire pump out of my scrap bin. I don't think I have to order any materials for this, which that always makes me extremely happy. I don't have all the dimensions that I need, of course, but I've got some oversized stuff, so this project is really going to put the subtractive in subtractive manufacturing. I'm going to start with the valve body that runs vertically at the front. The stock I have for this is quite a bit oversized, so we're definitely going to have to machine it down, but that's okay. Start by facing off the end, as is tradition, and also because it's going to give me a nice square surface into which I can put the center drill because we are going to need tail support. I've got lots of stick out here, but for a light facing cut, I got away with that. Brass is really fun on small machine tools because you can take really heavy cuts and make you feel like an A-bomb or a Curtis. You can cosplay as your favorite real machinist. Couple of heavy cuts and one finishing cut, and just like that we've saved ourselves a trip to the hardware store, or more likely, waiting 2 weeks for something to be shipped online. Yahtzee. With the OD established, I'm going over to the mill. I've got it in a collet block centered up, and I'm going to center drill and drill partway through this material for a fitting that goes on the front. This is the pump output. There's a drilled and slightly counterbored hole into which we're going to be soldering the threaded fitting. Now we can make that threaded fitting, so I've got a small piece of bar stock back in the lathe, face off the end, turn down the OD, and then we'll be drilling this through. This is a plumbing fitting after all, so it needs a hole all the way through, and that's where the water is going to go. The difference between a bar and a pipe is a hole down the middle. I know. This is the extremely technical content that I know you're here for. Write that one down. I actually need a very accurate depth counter bore now. So for that, I've got this set up on my tailstock. This is what I do when I need really accurate drilling depths. I've got a toolmaker's clamp on the quill and an indicator on that. And I can slide this around and leave it on there for long periods if I need to. And it's quite quick to set up. So I can touch the drill up against the material, then zero the indicator there, and then wind the drill back, start the machine, and wind in, and I know it'll start cutting right on zero on the indicator. Then I can get a drill depth down to the 1,000th quite easily. There's the little counter bore right there. Now we need to narrow up the neck behind the threads. This is what's going to fit into the hole that we drilled in the valve body, so I'm using a grooving tool for that. And then I'll chamfer the end, which will make it easier to cut the threads on the end of this, which forms the actual plumbing fitting. That then gets a generous chamfer on the end to clean up the threads, and it also makes it much easier to install and remove the plumbing fittings, and of course because chamfers are what separate us from the animals. And Yahtzee. That little fitting goes right in there on the valve body like so. We are now ready to silver solder that in place, so over to the hearth, get everything gooped up with flux, get everything assembled, get a little teeny piece of solder on there. And then I made an extreme effort to solder this at a very awkward angle so that my arm would not be blocking the camera, and in fact, it was a total fail and my arm was blocking the camera in 90% of this footage, so that's what you got. But trust me, the solder flowed, and then I rolled it around to make sure that the solder had drawn across to the other side, which it had, and cleaned it up a little bit. And it's not the prettiest joint I've ever made, but it's certainly sound, so life is good. The main part of the pump body is square, or rectangular I guess actually, but again I don't have the bar stock that is the correct dimensions for that, so I'm going to manufacture it out of this larger piece that I have. Once again, how you going guys? Insert your favorite YouTube machinist cosplay here. I left the end sticking out of the vise a little bit so that I could come right back in with an end mill and square up the end of this piece. The other end is going to remain rough cut because we are going to be cutting it to length later on. The next feature is a slot that goes down the center. This is like a tab and slot, or I guess a mortise if you like, for the foot that holds the pump upright. There's going to be a plate that goes down into this slot. Now from this same setup, I can center drill, pilot drill, drill, and ream the large bore that holds the valve body. This is getting reamed not because it's a precision sliding mechanism of some sort, but because we want a really accurate and precision fit around the column, because it's going to be silver soldered in place, and it's actually quite a large and complex joint. So the clearances on this joint have to be just right for the silver soldering to work. That's now a nice sliding push fit on the valve body. Next in the order of operations is to have Captain Vasily re-verify our range. 1 ping only, please. I've got some stuff to do on the other side, so I can use an end stop to flip the piece over, and I won't have to re-edge find on anything. My X and Y positions on the DRO will remain valid because the end stop is maintaining my X position, and the Y position, of course, is held by the fixed jaw on the vise. This side gets a little slot similar to the one on the other side. This holds a little triangular plate that forms the fulcrum for one of the linkages that controls the motion of the pump handle. To make all of the various plate elements now, I've got this piece of stock that I found in my bins. It's some kind of unusual type of brass that I haven't seen before. It's been in my bin for a really long time, but I got it with this really heavy patina on it, so it was on someone's shelf for an extremely long time. It's very hard stuff. It's certainly not 360 free machining brass, and it's not even like 280 hard plate brass like you normally buy. This is something even tougher than that. It might be like naval brass, something like that. I'm not sure. It's not a type of brass I've encountered before. It actually machines really well in the sense that the finishes on it are really, really beautiful, but it's definitely hard work for the machines. I have to take lighter cuts, and the burrs that it makes are really difficult to remove. So this is tough stuff. It almost machines like steel. I machined 2 parallel edges on this piece so that I could hold it in the vise like so, because I need to thin down this plate. This plate is a little bit thicker than the 2 pieces of plate that we need to make the 2 features that go in those slots that we just made on the pump body. This piece is a bit of an odd shape because I've rough cut it to the size to make both of the little pieces that are going to come out of this. Figured since I have to thin down the stock anyway, I might as well thin down the whole piece first, and then I'll cut the little bits out of it that I need. You can really see how hard cutting this stuff is. It's not like brass to smoke the coolant like that. This stuff is really putting up a fight. The end result, though, is actually really nice. The finish on it is just beautiful. It's a very dark yellow, whatever this is, so I'm no expert on brass alloys, but this is definitely one that I have not seen before. Now this slightly odd-shaped piece has been machined down to thickness, and I can glue it up and lay out the 2 pieces that I need to get out of this. I'm going to create the vertical upright that forms the first part of the foot of the pump, and then the little triangular bit will come out of here that forms the fulcrum for the pump handle. Per usual, those were rough cut on the bandsaw, and then all the edges cleaned up on the milling machine. The vertical standoff plate gets 2 very tiny number 080 screws drilled and tapped into the bottom of it, and this is going to allow us to fixture the other part of the foot for silver soldering later. These little screws will also add a fair amount of strength. There's a fair bit of force that's going to be on this foot in the end. I've rough cut the little triangular piece, but of course it has square sides and our slot has round ends, so those don't quite fit together. I decided to needle file this to shape for a perfect fit in that round-ended slot. You could of course just cut the slot wider, but you know, where's the fun and elegance in that? It was a fair bit of work, but as you can see, I got a nice rounded end tenon on that. And into the mortise it goes. See, I know woodworking stuff. And look at that. Isn't that a beautiful fit? That was super worth all the effort, honestly. That's very satisfying. I then rough cut the triangle shape into it, but I've left it oversized because I don't know exactly where the hole is going to be yet. The hole has to be drilled relative to the piston bore. That dimension is quite important. So we're going to leave it oversized and blank like this, and then we'll shape it a little bit more once the hole is drilled in it. You can see how the foot plate goes in there like so. I just made the slot for that foot oversized. I didn't want to file that one too. Next up is a Kozo trick that I really like. I don't know if he invented it, but I certainly learned it from him. And that is to put center punches between pieces that are going to be silver soldered together. In this case, I'm going to put 8 punches all the way around the diameter of the valve body. And what that does is it converts that loose fit that we had, or rather that sliding fit, into like a snug, kind of difficult to push fit, if that makes sense. But the point is that those punch marks are now holding a gap all the way around that valve body so that there's place for the silver solder to flow all the way down around that column. That's why we wanted it to be kind of a loose fit initially, or at least a 1/1000 slip fit, and now it's a snug fit with the punch marks, and the punch marks are kind of suspending it in space inside the hole. Everything now gets pickled and assembled with flux, of course. Put a little ring of solder all the way around the top of the valve body, and then I'm going to heat this only from below. And the goal is to get that solder to run all the way down around that column of that valve body and come out the bottom. This really needs to have a complete silver solder seal all the way around, or else there's going to be some sort of internal water or pressure leak in the pump, and it's not going to work efficiently. This actually took a while. That square valve body has quite a lot of mass to it, so going up a size on my torch would not have been a bad idea, but that required dragging the propane tank in from outside, and I wasn't in the mood to do that. But I did get the solder to flow really nicely after a bit of patience. And the best part is, after cleanup, as you can see, I got a really nice silver solder joint all the way around the top and all the way around the bottom. I got silver solder flowed all the way down, and I got to fill it around the bottom as well. So really that could not have gone better. That's an excellent joint all the way down in there. Then I silver solder the little triangle fulcrum piece on there. And finally that vertical plate for the foot as well. I don't show it all, but in between all of these parts, I'm pickling everything, cleaning everything up, fluxing for the next set of joints, and so on. If you want to know more about this whole process, watch this playlist from the beginning. There's the pump body so far. Now we've got excess length on the lower part of the valve body, specifically so that we can hold it like this in the lathe. This is a suggestion by Kozo in the book, and I followed his instructions here. From this position, we can now do all of the features required for the valve body in the upper part of this valve column. This is quite a complex series of operations. Start by center drilling and drilling all the way through, which forms the water passage. Then we open up the upper part of the valve body a little bit with a larger drill. Then we go in and we need to form the actual valve seat itself, which is a 15-degree lip around a counter bore. So to do that, we're going to need a special valve seat cutting tool. I found this old split blank in my drawer. It's just got a practice D-bit that I did on one end. The other end is my internal threading tool, so I'll regrind the practice end since I don't need it for anything. And of course, I'll use the D-bit grinder for that. If you don't have a D-bit grinder, you can do this with a regular piece of tool steel. Just cut and machine it to shape and then harden it when you're done. But, you know, I have a D-bit grinder and I have these carbide split blanks, so why not be all fancy? I mean, I'm wearing the apron and everything. I should at least look like I know how to use all these tools. I start with the workhead in free spinning mode because I need to reduce the diameter at the end of the tool to 219 thousandths, which is the diameter of the valve body. And that way, as the tool is cutting the valve seat, it's fully supported by the area around it, by the bore that the valve seat is sitting in. That'll make sure that it doesn't deflect and cut the bore oversize or something along those lines. With the shank on dimension, then I can swing the work head around to 15 degrees away from the wheel and 15 degrees towards me. And that's a compound angle then that creates the clearance under the cutting edge and the 15-degree face on the front of the cutting edge that is going to create the 15-degree angle that the valve seat requires. Geometry like this is where the D-bit grinder really shines. It makes it so quick and easy to make complex compound angles on cutting tools like this. It's really a joy for this type of thing. This is the moment where I realized I'd cut the angle on the end of the tool the wrong way, because of course I had. I needed to angle it 15 degrees away from me. So I did that and reground the end of it. Stay in school, kids. Angles are hard. But after a fun 10 minutes at that machine, we now have one custom 3.5-inch gauge check valve seat cutting tool. If nothing else, that D-bit grinder sure does make pretty tools. Look at that. Solid carbide. Like nothing. Back to the work still in the lathe now, and I can feed this tool in. It acts a little bit as a boring bar as well. It's going to self-clearance. The pilot hole that we gave it is actually intentionally a little bit undersized, so it's just cutting a few thousandths off that bore, and then when it gets to the bottom of that bore, it's going to cut the valve seat with the 15-degree end on that tool. So it creates kind of a 15-degree dome shape, if you like, towards the center of the bore. And that's what the ball bearing is going to sit down on to form the seal. To form the actual perfect seal itself, there's one more step that we're going to be doing, but stay tuned for 1 second on that. Then the very topmost section of this bore gets threaded for a sealing plug that will go in here. The valve body is accessible in the future for servicing, but we need to seal it up when in normal use, and that's what those threads are for. Lastly, I need a counter bore just above those threads, but I don't have a boring bar small enough, so it's back to the D-bit grinder. This is a lot of work for one cut, but actually I've been needing a really small boring bar for a really long time, so I finally said enough is enough. I'm just going to stop right here and go make one. So I grabbed, this time, a piece of high-speed steel because I had a broken center drill and one of those long-reach center drills, and I just ground this down into a teeny tiny boring bar. Wait, hold on. Just waiting for all the watchmakers to stop laughing. Yeah, I know it's bigger than any boring bar you own, but it's the smallest one I now own by quite a bit. This counter bore might not seem like much, but it's actually quite important. It's only 50 thousandths deep, but it forms a really sharp right angle at the top of this bore, and that right angle sits against a taper in the plug and is actually what seals the top of the valve body. There's no gasket or O-ring in the top of this. It's just two machined surfaces that seal this. It does work. It's actually quite clever, but it does require an accurate square corner right on this top edge, hence the boring bar and then facing it at the end. Here's a look at all the features we just created. Sorry, I thought I'd cleaned all the chips out better than this, but you can still kind of make it out. In the center, of course, we have the water passage, and then just above that is the 15-degree angle away from center that creates the valve seat. Then there's a smooth bore section above that, which is where the ball bearing rides, so it doesn't get snagged on anything. Then above that, there's a section of threads, which is where the plug threads in. Then above that is the counter bore that forms the sealing corner that the plug seals against. It's a lot of features all in about a half-inch of space, but that's how model engineering goes sometimes. When you're making tiny mechanisms, you got to create lots of tiny complex features. And by the by, I did a test piece with all of the operations in that valve body, both for practice and also to test the new cutters that I made. You never want to test a new cutter on your actual workpiece because you need to learn how that cutter cuts and whether the angles and geometry are right and so on. We need to work on the other end of the valve body now, and Kozo recommends chucking it the other way using a similar technique to what we just did, holding it thusly in the 3-jaw. However, Kozo's chuck is clearly smaller than mine because while this works for him, it does not work for me. There isn't enough clearance around all of the features on the top of the pump here, and when I try to hold it in my 3-jaw, it can't be successfully held concentrically because of all of the interference. So I cannot do this on my lathe the way he recommends, so I'm going to take it over to the mill and do it here instead. Start by squaring up the end. All of the delicate boring and valve cutting operations and so on that we needed to do on the bottom are much easier to do on the lathe, which is why that was done there. But we can get away with doing this side on the mill because it's pretty straightforward. I centered it up using my coaxial indicator. This is certainly an overkill tool for the hobbyist. You can do this with a DTI and a spindle clamp just fine, but this thing was a birthday gift from me to me, love me, a few years ago, and it's a lot of fun to use, so I'm going to use it. This end gets drilled and tapped like the other side. The threads on this side are for the pickup, the intake of the water pump, not a plug like on the other side. The catch on this side, though, is we have to do the same accurate counterbore with a boring bar like we did on the other side, because the pump intake has the same kind of taper seal that the plug uses. And I don't have any way to create that counterbore because I'd have to use a boring head since we're on the mill, and my boring head won't take boring head small enough to do this. However, I happen to have a weird sized reamer the exact size that this counterbore needs to be. So I can get away with doing this with a reamer. Counterboring with a reamer, not super common, but because the counterbore terminates in a thread, the tapered end of the reamer is going to create a 45-degree angle that's just going to kind of blend into the thread. Most of the time when you're counterboring, you want a square shoulder inside, so you couldn't use a reamer like I just did, but I got away with it this time. Now finally, we can make the business feature of this pump, which is the piston bore. I'm going to set it up in the 4-jaw chuck, which of course requires indicating in rectangular stock. If you are interested in how to do this, I covered it in my video on 4-jaw chuck techniques. But the TLDR is you rock it back and forth to find the low point on each side, and then you know that side is vertical, and you take a reading, and you repeat until all sides are dialed in. It's the same as dialing in round stock, it's just that it's a little bit slower because you have to find vertical on each side before taking the reading. But I managed to get it to within 1,000th on both axes without too much difficulty. Let's spin that up and see how it's running. It might be a bit off balance, but actually no, that's not bad. The foot is not creating enough of an off balance mass to really create any issues. So I can center drill now and pilot drill this. This is a very deep hole. It's a very high aspect ratio hole, which is to say much deeper than the diameter of the drill. So it requires clearing chips extremely frequently. If you don't clear chips frequently, then they jam up in the hole, which can cause the drill to overheat and cause the drill to wander off course and cut the hole crooked or oversize, usually both. Then next I can come in with a larger drill to clear out the bulk of the material, and this is going to cut nice and straight because we did that pilot drill first. This drill is large enough that the high aspect ratio is not a problem for it, so it can clear chips just fine. For all these operations, I've got my dial indicator set up on the tailstock as you saw before, of course, because depth needs to be quite accurate. Quick sanity check on my depth from that pilot drill, and that looks good. We're right on the money. Now I need to come in and bore this thing out. However, the boring bar that I have that will fit does not have enough reach to get all the way in. The shank on this boring bar thickens too soon and I can't get in deep enough. So instead I'm going to try something else. I could grind down that boring bar, but I hate to do that if I don't need to because it's going to weaken it for future cuts. So instead I'm going to ream this because once again I happen to have a reamer that's the exact dimension for this bore. Now using a reamer here instead of a boring bar means that I'm not going to have as good concentricity, but the concentricity of this bore relative to other features actually doesn't matter that much, so this reamer will still get me within 1,000th or 2 of perfect concentricity. Boring is always better than reaming for concentricity because the reamer is going to follow whatever the drill did, whereas the boring bar is going to carve its own path concentricity-wise, and it can correct any errors caused by the drill. The reamer can't do that, but in this case, reaming's just fine. And well, spoiler alert, here's the piston that I've already made, which I'll show you later, but I just wanted to test fit it in the bore, make sure we've got a good sliding fit, no play. This doesn't have to be an air pressure seal because there is actually an O-ring on this as well. It just needs to slide easily. Speaking of that seal, we need a bronze bushing that goes in here and it seals an O-ring up against the piston. So for that I can use my boring bar because I don't need much depth, and I can bore this out nice and concentrically. The O-ring sits inside this counterbore and then it's pressed into place by a bronze ring that we'll be making later. Again, it would have been better to do both those features with the boring bar because then they would be perfectly concentric to each other. Because I bored one and reamed the other one, they might be slightly off, and in fact they were slightly off by about 1,000. So I did have to do a little fitting at the end when this pump was finished, but it wasn't enough to cause any functional issues with the pump. It just required a little more massaging on final assembly. Now this bore is too big for my largest gauge pin, but I was recently donated this lovely inside micrometer thanks to the Toronto Model Engineering Club. Thank you, gents, for sending me some tools. That was the perfect thing here because it's too small for my telescoping bore gauges, too big for my gauge pins, and this is why machinists all die in giant buildings full of tools. You can see the vice jaw has chewed up the end of that pump body, but that's okay because that all gets cut off. That was extra length just for work holding. So that got cut off on the bandsaw, and then I cleaned up that end on the milling machine, and we're getting close to finished on this pump body. Now that we have the bore, we can finally drill the fulcrum point for the linkage that controls the motion of the pump handle. So I'll set it up like this in the vise. I'm going to be drilling really close to the top of that vise jaw, so I've got a little bit of ablative drill armor in the form of shim stock, which is spring steel, and well, good luck drilling through that even when you're trying to. The most important thing though is we have to reference from that bore. So I've got a gauge pin that's an extremely close fit in that bore, and I can edge find on Y to center up on that bore, then pick up the edge of the pump body, and now I've got enough information to make my translation to where this fulcrum hole is supposed to be. And I can center drill, and ream this all the way through. At this point you might be thinking, hey, that hole looks like it's nowhere close to where the shape of that tang suggests that it should be. And you're right, it is nowhere close. Now I quadruple checked the position of that hole, and the position of the hole is correct. So I just made this triangular piece way oversized somehow. I'm not really sure how that happened, but in my defense, the drawings had basically no dimensions on that triangular piece, so I had to deduce it from a lot of other things, and well, I did intentionally make it a little oversized so I would have material to remove, but careful what you wish for, because now I had a lot of extra material to remove off of this tang. I cut off the worst of it with the fret saw and then did my best to finish it up on the die filer. Because it's so oversized, the shape ended up not being really correct either, so it's certainly not pretty, but it will be functional. And as I said, before I did all of this cutting, I made very, very sure that it was the hole that was correct and not the shape of the tang because, well, I don't want to do all this again. The final fulcrum bit is pretty ugly, but as you can see when I install this linkage that you haven't seen me make yet, it's completely covered up anyway, and it's very functional. Nothing's going to interfere with the functioning of the pump, and this pump is going to spend its entire life inside a water tank, never to be seen again, so it's not worth a lot of effort redoing that, ugly though it may be. Now to finish up those valve seats. This part's really cool. I've got a custom-made brass drift with a dome in the end of it. It's the same diameter as the valve body, and it holds the end of the ball bearing like so. Ball bearing goes down in the hole, the drift goes down on top of it, and then we just give that a light tap. And what that does is that ball bearing crushes the top edge of that 15-degree angle that we created, and it forms to the surface of the ball bearing. Now if I try to blow air through it one way, nothing. No air moving. Suck back the other way. Yep, air moving. Blow the other way. No air at all. So that works perfectly. Now, when doing the suction test, tread lightly because your lungs have a finite number of ball bearings that they can hold, and that number is 0. Trust me, that's not a conversation you want to have with the emergency room doctor. Some people say this channel sucks, and well, they're right, but it doesn't blow. Final step then is to attach the foot onto the body of the pump, thus completing the support system for the pump where it sits on the floor of the tender. Remember, this has tiny screws in it to hold it in place for silver soldering and also for additional strength in the final assembly. Very straightforward silver soldering job here. Flux, pickling, silver solder, heat, yada yada. Heating mostly from below, with a little bit up on the sides to try and heat everything evenly. We've got a pretty uneven distribution of mass on this pump body now, so there was a little bit of skill required in where to put the heat. A little bit of cleanup, and there is the final pump body, all ready for all of the little bits that get attached to it, of which there are many, of which we still need to make, but which will have to be in a second video because we ran out of time in this one. I wanted to show you the whole pump, but my union is telling me we have to stop. So, thank you very much for watching. Thanks especially to my patrons for making all of this content possible every single week, and I will see you next time.